Hello, and welcome to lesson 14 of this Introduction to Probability of Wolfram. The topic for this lesson is the Poisson distribution. Let's begin. This distribution is discrete, but interestingly enough, it's also on a continuous sample space. It can be seen as a special case of the binomial distribution, where n tends to infinity. But why is it called Poisson? If you know your French, you'll notice Poisson actually means fish. But this has nothing to do with the actual distribution. No, in fact, it's only called that because it was introduced in 1837 by the French mathematician Simeon Denis Poisson. In this lesson, you'll see how to compute Poisson expectation, probability, estimation, and simulations. Okay, let's think about it. If there's an infinity of Bernoulli trials occurring, then n is huge, but to balance it out, p has to be very close to 0, so that the average, n times p, is a reasonable constant. You don't need n or p in this context, but just the average, which we'll call mu. Consider these two mathematical statements that you'll need in this proof, and notice that one of them is an approximation. Okay, now take the PDF of the binomial, then isolate the terms in n with that function, then replace that part, and finally approximate using the second statement. If you check the PDF of the Poisson distribution, this is indeed what you get. Visualize it by using manipulate on a discrete plot of the distribution. Notice this distribution only has one parameter. The cumulative distribution function, like the binomial, has a sum that can't be algebraically reduced. So the CDF uses the gamma regularized function. Of course, you can plot this as easily as the PDF. If you followed the logic so far, the Poisson distribution is a special case of the binomial distribution, so all its formulas, properties, and characteristics should be subcases of the binomial. For example, the mean of the binomial is NP, so the mean of Poisson should be mu, which is equal to NP. Then for the variance, the binomial is NP times 1 minus P. Since P tends to 0 in the Poisson context, then 1 minus P is actually 1 minus 0, and so 1. And so the variance is mu, as you can see here. So why use the Poisson distribution? Well, you need discrete events on a continuous sample space, like the number of flights per day or the number of squirrels per acre of land. And you also need a constant rate of occurrence. More practically, though, this distribution is designed for relatively rare events, like natural catastrophes. Common sample spaces for Poisson distribution include time and distance. Okay, time to apply this knowledge. If there's an armed robbery every 5 minutes, what's the probability 4 armed robberies happen in the past 10 minutes? Okay, so there is one armed robbery every 5 minutes, so there should be, on average, 2 armed robberies every 10 minutes. And so that's your frequency, mu. Then take the numerical probability at 4 with Poisson distributed at mu 2, and you get the answer. How about another situation? Let's say when you arrived at the train station, you started a timer. You know that on average, 7 trains pass every hour, and so far you've seen 3. So, what's the probability that you see at least 5 more trains before your timer reaches 1 hour? Well, simply take the probability of x, at least at 5 plus 3, which is 8. Given x is at least 3, over the Poisson distribution where mu is 7, and you get the probability. Let's combine some Poisson distributions. You're fishing with your 2 friends, Sarah and Anil. On average, you catch 4 fish per hour, Sarah 3 and Anil 2. If you all fish for 4 hours, how many fish do you expect to catch altogether? Well, just take the expectation of the sum of fish each of you caught, where your distribution is 4 fish times 4 hours, Sarah's distribution is 3 fish times 4 hours, and a nils distribution is 2 fish times 4 hours, and you get 36 fish. Imagine a manufacturer buys 30 machines of $3,000 each. Each machine earns the manufacturer, on average, $50 per hour. But there's a cost. You see, every week, on average, two machines break down and are replaced. How many weeks are expected to be needed for this venture to start making profit? Well, just imagine for a second that we know the number of weeks is W. So the hours for the earnings will be 24 for every hour times 7 for every day in the week, and so times W. And the machines break down twice a week, so 2 times W. So the profit function is the cost of buying 30 machines plus 50 times the earning hours minus 3,000 times the machine failures. Now that you have an expression in W, solve the expression when it's equal to 0, that is, a net 0, for the variable W. And you get the answer, that you should expect that it takes about 37.5 weeks to make a net profit. What about simulating Poisson? Well, you could just use the random variate function. You can also plot it, setting the plot range to see absolute changes clearly and see how the distribution varies as mu varies. Notice n here is just the sample size. What about a situation where you have data that seems to be Poisson distributed? For example, the rate of scientific discoveries recently seems to be Poisson distributed. Okay, well, load the data, aggregate it, adjust for relative frequency, estimate the distribution, and show the estimated distribution against the data. This result is not trivial, but historical, since this paper actually helped popularize the use of Poisson distribution in statistics today. Notice when p is very small and n is very large, the binomial distribution obviously approaches the Poisson distribution as it gets closer to infinity. Since the Poisson distribution is easier to compute, it's sometimes useful to approximate the binomial using the Poisson distribution. Here you can see a decrease in p helps distributions to agree. So what should you remember? The Poisson distribution is based on an infinity of Bernoulli trials, which practically results in a discrete random variable with a continuous sample space. Use Poisson distribution, probability, expectation, random variance, and estimated distribution functions to solve Poisson distributed problems. This distribution can also approximate the binomial distribution when p is small. In this lesson, we reduced the scope of the binomial distribution by taking a special case. But in the next lesson, you'll generalize the binomial distribution by including more variables.